All right, so let's work on some chapter 6 homework here. All right. So, number 3. You want to read that one for us?
FM 95 and FM radio station broadcast at 90.51 times 10 minus 7. What are those units?
Per second. Per second. So that's frequency. That's its frequency.
Okay, parentheses, 95.1 megahertz, is that what that says?
Yeah.
What's the wavelength of these radio waves in meters?
Okay, good. So we want the wavelength in meters, and we're given the frequency. Okay. So in class and in the videos, we've talked about the relationship between wavelength and frequency. Wavelength times frequency equals the speed of light. Electromagnetic energy all travels at the same speed, all right, under the same conditions, and that speed is what we call the speed of light. That is roughly 3 times 10 to the 8th meters per second, all right. So if we're going to use that as our speed of light, it gives us an indicator as to what units we have to be dealing with, all right. So we want the wavelength in meters, right?
Yeah.
So that's nice. We know we want this in unit of meters. What does that mean that the units for frequency need to be to make the units on the left side of this equal sign the same as on the right?
Oh, you mean like per seconds?
That's right. See that? Those are called hertz. Meters times per seconds will give us meters per second. All right, and it gives us right there 9.51 times 10 to the minus 7 per second. So that just needs to go in here, right?
Yeah, sounds good.
Whoops, times 10 to the 7, sorry, not the minus 7. So I'm going to do 3 times 10 to the 8th divided by, get this m by itself, 9.51 times 10 to the minus, or not minus 7, just 10 to the 7th. Okay, so remember, work your calculator if you haven't figured out how to do that yet. This will be one where the order of operations will get confusing if you're not writing the scientific notation correctly. So the answer here is 3.15 meters. All right. So that's the wave's length, right, for that radio station's electromagnetic frequency, or electromagnetic wavelength there, 3.15 meters. All right, 2, light with a wavelength, number 5. Light with a wavelength of 614.5 nanometers looks orange. What's the energy in joules per photon of orange light? Okay, so let's see if we can get this one. Let me fix up this just a wee bit here. Drag this off the screen so it becomes less distracting. Okay, there we go. So we want energy, right?
Yeah.
So there's an equation that we have to become familiar with as well. And generally this equation will be kind of provided for us if we ever need it. But it's that the relationship between the energy for a photon of electromagnetic energy is equal to its
Frequency.
frequency times Planck's constant. Planck's constant times its frequency equals its energy. Good. Now, what is Planck's constant?
Wasn't it something times 10 to the, oh, I can't remember.
Let's look it up. Okay? Planck's constant?
According to
There it
TechTarget,
is,
in the
6.6
International
times 10 to the
System
minus
of Units,
34.
the constant value is 6.626070015 times 10 minus 34 joule hertz minus 1.
Okay, did you hear the units there?
Well, something about joules.
Okay. So the units are Let me bring that back up here. Units are joules. Sorry, the units for Planck's constant are joule seconds. Joule seconds. All right. So the units for energy are joules. The units for frequency are per second. All right. We just talked about that. So joule seconds, joules times seconds, divided by seconds will leave us with just joules. Or sorry, times by seconds, times by frequency, which is dividing by seconds, will leave us with just joules. Okay? So this unit here, meters squared per kilogram per second, is the same as joule seconds. All right? We won't get into that unit, how it's how it relates to this. But Planck's constant is in units of joule seconds. Now we need that number, 6.63 times 10 to the minus 34. There's our Planck's constant, and that's joule seconds. And per seconds, what is our, let's see here. Oops. What is our frequency?
Oh, they gave us a frequency?
Yeah, right here, right?
Oh, no, they gave us a wavelength.
Oh, they gave us a wavelength. Okay. So they gave us a wavelength. Let me fix here. So they gave us a wavelength. And we want a frequency so that we can plug the frequency in here. So we need to use the speed of light, 8 times 10 to the third meters per second. Set that equal to our wavelength, 614.5. Now, it's nanometers, but I'm just going to call it times 10 to the minus 9 meters, because I want units to be in meters, because this is in meters per second over here. So that this will give me the per second frequency here when I take the speed of light and divide it by the wavelength. Okay? So, 3.8 times 10 to the minus 8 times 10 to the minus 8 times 10 to the third divided by 614.5 times 10 to the minus 9. All right, so that gives me 4.88 times 10 to the 14. And that's the frequency that I can multiply by Planck's constant to get the energy.
So you just multiply that by Planck's constant?
Yeah, just multiply that by Planck's constant. 6.63 times 10 to the what?
Minus 34.
Minus 34. All right, so 3.3 times 10 to the minus 19. 3.3 times 10 to the minus 19, that is in joules. 3.3 times 10 to the minus 19 joules. That's our energy. Okay, good.
So do we have to convert that to electron volts like it says?
All right, so it says what is the energy in electron volts? And it says right here that energy, 1 electron volt is that many joules. I trust that you can do that conversion, but I'm not going to be working with electron volts in this class. We're just going to be working with joules. Okay, so number 7. A photon of light produced by a surgical laser has that much energy. Calculate the frequency of the wavelength of the wavelength of the photon. What's the total energy in 1 mole of photons? Calculate what is the color of the emitted light. So apparently it's going to be in our visible visible range, if it's going to have a color. Okay, surgical laser has an energy of that many joules. All right, 3.027 times 10 to the minus 19 joules. So what can that do for us?
Well, we got the energy from the joules. Can we get the? We got the energy from the. We got the energy from the frequency last time.
That's right. So if we have the energy, we can get the what?
Probably the frequency, right?
Yes, the energy equals Planck's constant times the frequency. So if we just take this energy and divide it by Planck's constant, we will get our frequency. And once we get our frequency, what can we do?
Well, the frequency times the wavelength is the speed of light.
That's right. Frequency times the wavelength equals the speed of light. So 3 times 10 to the 8 divided by our frequency will equal our wavelength. All right, so let's find our frequency by taking the energy divided by the Planck's constant. All right, so we got Planck's constant here, 3.027. That's our energy, times 10 to the minus 19. There's our energy in joules. And our Planck's constant is 6.63 times 10 to the minus 34. All right, so we got a frequency of 4.57 times 10 to the 14th. Is that one of the questions?
Yeah, they ask us what the frequency is.
So the frequency equals 4.57 times 10 to the 14th, and that's per second. All right. And now we need to take 3 times 10 to the 8th.
The speed of light?
Yeah, 3 times 10 to the 8th. Divided by our frequency there, right?
Yeah.
And that will equal our wavelength, which is 6.57 times 10 to the minus 7. What are our units?
I don't know.
Well, this was what? What are the units for this?
That's the speed of light. Is that meters per second?
That's right.
Oh, so that must be in meters then, huh?
This thing's in meters. That's right, because this is meters per second, and this is per seconds. All right. Now that gets a little confusing, but meters per second divided by per second. That's the same as taking meters per second, timesing it by seconds over 1, so the seconds cancel out, and I'm left with meters. A little bit of math that we have to revert back to remembering how to do there, right? Okay, so that's in meters, 6.57 times 10 to the minus 7 meters. Looks like it's going to be 657 nanometers, is that right?
Oh, yeah.
Okay, so what do you think? What color is 657 nanometers?
Well, 400 to 700 nanometers, that's the visible light.
That's right, 400 to 700.
And 400 is like the violet, right?
Yep,
700 is red.
yeah,
So it's pretty close to red.
that's right. It is. It's pretty close to red, so it's probably reddish orange, leaning more towards the red side. Okay, good. Oh, now what is the total energy in 1 mole of photons? Okay, well, this is the energy joules for 1 photon. Okay, if I want to know in 1 mole of photons, right, this is 3.027 times 10 to the minus 19 joules per photon. And if I want 1 mole of photons, I take my Avogadro's number, because that's how many photons there are, right? There are 6.02 times 10 to the 23rd photons in a mole of photons. And I could have said 1 mole, and then take it to that many photons, but either way. And that will give me how much energy. So, we'll do that really quick. 3.027 times 6.02 times 10 to the 23rd. Okay, so it's going to be 182 kilojoules of energy in 1 mole of those photons. Okay, good. Okay, so I'm just checking here to see if what color they said. Yeah, they said red. That's reddish orange. All right. So, 35. Identify the subshell in which electrons with the following quantum number are found. All right. So, N equals 2, L equals 1. How do we know which one of these numbers relates to the subshell?
Subshell, is that I can't remember, is that N or L?
It's L. L is the subshell. Our subshells are the S, P, D, F, letters, those are our subshells, they correspond to L equals, do you remember?
1, 2, 3, and 4.
Well, almost. 0, 1, 2, and 3.
Oh yeah, we started 0 for S.
Okay? So L equals 0, 1, 2, 3, and 4 corresponds to these SPDFs. Those are just letters that we use to represent L equals 0, 1, 2, 3, or 4. And it's just to kind of simplify when we're talking about our N value and our L value. Okay? So, when we have L equals 1, that's a P subshell. All right? When we have L equals 2, that's a D subshell. When we have L equals 0, that is an S subshell.
So the N's don't change that?
They govern, the N governs what the L's possibilities are, right? So if N equals 2, for example, there are 2 subshells, and that can be 0 and 1. If N equals 6, there are 6 subshells, which can be 0, 1, 2, 3, 4, or 5, right? But if we just know the L, all we need to know is the L value to know what the subshells are. All right, so 37, identify the subshell in which electrons with the following quantum numbers are found. I guess what they want us to do, though, here a little bit more is L equals 2, that's D, but this N equals 3 would be a 3D subshell. All right, 1, 0, so what do you think?
Is that a 1S?
That's right, that would be a 1S subshell. 4L or 4L. Well, sorry. What do you think the answer is?
L is 3, so that's F, right?
That's right. So it's a 4F, right?
Yeah, 4F.
Okay, good. Write the set of quantum numbers for each of the following electrons with N equals 4 in a selenium atom. All right. So if I have a selenium atom, let me bring up my periodic table here. The best way to get to my periodic table. Let me try to search it here. There we go. Okay, so I have my periodic table here. I'm looking for selenium. Okay, and I need to write the set of quantum numbers for each of the electrons with an N of 4 in the selenium atom. All right. Sorry, here's selenium. There we go. So let's write really quickly the noble gas electron configuration for selenium. Do you remember how to do the electron configuration?
I can't remember what that means.
I'll do an example for you. For lithium, the electron configuration is 1s2, 2s2, or no, 2s1. 1s2, 2s1.
Oh yeah, okay, I remember that stuff.
All right, so if we're going to do an electron configuration for selenium, but we're going to use the noble gas core. Do you remember what that means?
Well, you start with the noble gas closest to it?
Well, the noble gas closest going backwards. So selenium has an argon core with these electrons outside of that argon core. So the electron configuration for selenium is argon core. And then we have what?
4s2.
That's right, 4s2. Fourth row, 2 electrons in the S block, potassium and calcium. Then we go to 3D, right?
Yeah, that's 3 along the D row there.
3D, and then we fill up all 10 electrons, 3D10. And then we're here to do what?
Is that 4p again?
That's right, we go back to 4p. 4p, and we do 4 electrons for selenium. All right? So what it's asking us to do is to write the sets of quantum numbers for each electron with an N value of 4. So we should have 6 sets of quantum numbers here. Okay, 6 sets of quantum numbers. We have, because we have 2 electrons with N value of 4 there, and 4 electrons with an N value of 4 there. So 2 electrons here. N equals what for these 2 electrons?
That's the 4, right?
Yeah, N equals 4. 1 electron has a 4. What's the L value here?
S is 0.
Right, if it's a S, then the L value is 0. And we can just remember this, right? L for 0, 1, 2, 3. S is, or the letters are S, P, D, and F. Okay? M sub L. What's M sub L?
I can't remember what M sub L can be.
M sub L can range between negative L and positive L with all the integers in between. So in this case, it could be negative 0 up to positive 0, or just in other words, 0. All right? Because M sub L can be whatever L is, positive or negative, and all the integers in between. Okay, so that's the limitation there. And then M sub S, what is it?
Oh, it's positive 1/2 or negative 1/2.
Right, and we'll just leave it positive 1/2 because the other electron in that orbital is going to have the negative 1/2. All right, so yeah, we can, no 2 electrons can have the same quantum numbers, right? And that spin, one orbital, you're going to have 1 electron with 1 spin and another electron with a 2nd spin. All right, so there's 2 electrons. Then we have 4 more. All of these 4, 1, 2, 3, 4, have an N value of 4. Can you see that?
Yeah, I see that.
So these 4 electrons. And what is their L value?
It's 1, right?
Good. L is 1. Okay, for these 4 electrons. Now, we knew that because, again, how do we know that?
P corresponds to 1.
That's right. The P block corresponds to 1. All right, what is the M sub L value?
M sub L value can be negative 1, positive, negative 1, 0, or positive 1?
That's right. It can range between negative L all the way up to positive L. So if we give this negative 1, this one we'll give it 0, and then this one a positive 1, and the last one could be any one of those 3 because it doesn't matter. They're degenerate, meaning their energy is different. It doesn't matter which one it fills first, but we'll put the second one into the negative 1 because we put that first one there. All right. So these can all have the same spin. They don't need to have different spins, except for this one, I guess. This one goes into that orbital, has to have a negative 1/2 if that first one had a positive 1/2. All right, so there we go. Those are those sets for the 6 electrons in a selenium atom that have an N equals 4 value. Okay, which atom has the electron configuration described here?
Is there an easy way to do this?
There could be. If we bring this up here and we see that it's got 4 P6, this is our 4, here's our P, so it's got a krypton core. And then it says we have 5s2 and 4d2. I would have put those in different order. Sometimes people like to put them in that order. 5s2 are right here. And then 4d2. So it has 2 of these 4d2 electrons. Oh no, that's right. Yeah, 5s2. That's the order I would have done it in. 5s2 and then 4d2. So it looks like we're talking about zirconium.
Okay, yeah, I can see that.
All right, good. Excellent. 56. Which atom has the following electron configuration?
Let me do this one. So we got 4s2. That's calcium down there. We got 3d7. Okay, so 3p6, after 3p6 should be 4s2, right?
Yeah, that's right. So I would have put the 4s2 before the 3d7 in this scenario.
But then we go across 7 in the 3d.
That's right. 1, 2, 3, 4, 5, 6, 7. So that looks like it's cobalt then, right?
Okay, sounds good.
Did I count right? 1, 2, 3, 4, 5, 6, 7. Okay, good. Which ion with a positive 1 charge has that electron configuration? Okay, so here we have one with a positive charge.
How does that thing change things?
Well, the number of electrons that the species has is one less, and so we have to think about it with what the atom would look like if it had one more. All right, so we can do the same thing. We can go to our 4s2, 4p6. Those are our outer shells. Here's our 4s2, 4p6. All right, so it doesn't have any, oh no, there it is, 3d10. So again, this was out of order in my perspective because it would be 3p6 followed by the 4s2 and then the 3d10 and then the 4p, 1, 2, 3, 4, 5, 6. So it has a noble gas electron configuration right now. But if it has 2 extra electrons, then it means that we're talking about a selenium atom or a selenium ion. Oh, wait. No. We have 2 questions here. Which ion with the +1 charge has that electron configuration? Krypton is the electron configuration. So with the +1 charge, that would be a rubidium atom. Rubidium atom, remove an electron, it has an electron configuration of this. That's krypton. Which ion with the -2 charge has that configuration? That would be selenium. So the first question is rubidium, and then the second one there is selenium. Did you follow that?
I think I got that.
Okay. So selenium, what would selenium's electron configuration be?
1 is 2, 2.
Well, do the noble gas electron configuration.
Okay. Selenium would be
Let me write it down here for you. Go ahead.
argon. 4s2. 3d10. 4p4.
That's right. 4p4. Okay. That's selenium. Selenium with 2 extra electrons would be same thing, argon, 4s2, 3d10, 4p4, well actually not 4 anymore, we have 2 extra electrons, 4p6. Okay? Rubidium, yeah, rubidium. Rubidium electron configuration is argon with, no. Krypton. Rubidium is krypton first. Rubidium is krypton with 5s2. 5s1. 5s1, right?
Okay, I follow that.
Rubidium is krypton with 5s1, and if we remove an electron, and that's what you get when you get the +1 charge here, then the result is just the argon's noble gas configuration, which is that. Okay, which of the following atoms contains only 3 valence electrons? Valence electrons. Okay, so there's a couple ways to do valence electrons. A lot of people learn in high school about valence electrons relatively early on. Okay, and a really easy way to do it is just to count these columns of the representative elements. Remember the representative elements, which blocks they were?
Not really.
So these first 2 columns and these last 6 follow some patterns really well, and they represent some rules in chemistry. So we call them representative elements, right? And if you have an element in one of these columns, then you can just identify the number of valence electrons simply by the column it's in. So lithium has 1 valence electron because it's in the first row. That's one way to think about it, and that's a lot. People learn that in chemistry relatively early on. If I look at the electron configuration for lithium, and I use the noble gas core, helium, lithium has a 2s1, and all the electrons with the highest N value are what we call valence electrons. All right. in an electron configuration.
All the electrons what?
All the electrons that have the highest N value. So lithium has a 1s2, 2s1, and this is one electron with the highest N value. That has lower N value, right? So that would be the number of valence electrons. So if we look at boron, right? Boron, 1s2, 2s2, 2p1. These electrons are the ones with the highest N value, so I have a total of 3 valence electrons. Or you can just count the columns over, not including just of our representative elements, not our transition metals here. Okay, and boron's in the third, so it's going to have 3. Nitrogen,
You're gonna have 5?
that's right, nitrogen's going to have 5. 1, 2, 3, 4, 5, right? And the electron configuration for nitrogen is,
A helium atom?
that's right, a helium atom.
2s2, 2p3?
That's right, 2s2, 2p3. So there's 5 electrons with the highest N value. Okay, so fluorine has how many?
7.
And neon?
It has no valence electrons?
Yep, it has a full 8, right? So 8 valence electrons. Okay, good. Which of the following has 2 unpaired electrons? Unpaired electrons. So now we have to talk about what this means to have paired and unpaired electrons. Okay. To do this, we need to draw what are called orbital diagrams. Orbital diagrams. Magnesium, we look at the electron configuration. We use the noble gas. It has, so magnesium has a neon core with 3s2. How many valence electrons?
Is that just 2?
That's right, just 2 valence electrons. Okay, so magnesium, neon, 2 valence electrons. To write the orbital diagram here, we could start with 1s, 2s, 2p, 3s, right? The 2p has 3 L values, sorry, M sub L values, -1, 0, +1. Okay, for magnesium, there's 2 electrons in 1s, 2 electrons in 2s, 6 electrons in 2p, and 2 electrons in 3s. All right, this is energy. This is what we call an orbital diagram, and it's just relative energies of these different shells or subshells as we move up, right? Now, here, when we have elements like, let's say, sodium, this is magnesium. But if I were to do the electron configuration for sodium, right below here, it would have 2 electrons in the 1s, 2 electrons in the 2s, 6 electrons in the 2p, and then only 1 electron in the 3s. And we say that that electron there is unpaired. Unpaired. So when we're talking about unpaired electrons, it's electrons that only have 1 electron in a given orbital. So this is energy. This is the electron configuration, or sorry, the orbital diagram for sodium. Sodium's electron configuration is neon atom with a 3s1. Okay? Good. So which of the following has 2 unpaired electrons? Does magnesium?
I don't, does it?
Well, all of these electrons are paired up in all their orbitals. So no, magnesium does not have 2 unpaired electrons. It doesn't even have 1 unpaired electron. Okay? But let's look at silicon. 14 electrons, neon core, 3s2, and then 3p2, right? 3s2, 3p2, neon core. And this is the electron configuration for silicon. So does it have any unpaired electrons?
I still can't tell how you know.
All right, so we draw our orbital diagram. Neon, I mean, within here, everything's filled. So I could just write neon. I'll write it from now on, I will, but this will be the last time I'll show you. 1s is filled, and 2s is filled, and 2p is filled. So there's my neon core. All right. Now, next I have 3s, so I could have just represented this by saying neon. Now I have 3s and 3p. How many electrons in 3s?
2.
How many electrons in 3p?
2.
That's right. Now Hund's rule says that you don't pair up electrons until every orbital in a subshell has an electron. So there we see that I have 2 electrons that are what?
Unpaired?
That's right. So silicon is a scenario of having 2 electrons unpaired. Okay? Now I can convert this really quickly to sulfur, right? I just have to do what?
Add 2 electrons.
So that's 3p4, 3, 4. Do I have 2 unpaired electrons now?
Yeah, you do. You still do.
That's right. So sulfur has 3 unpaired electrons as well, or 2 unpaired electrons as well. So my answer is both silicon and sulfur, isn't it?
Yeah, that makes sense.
Okay. Which atom would be expected to have a half-filled 6p subshell?
6p?
Yeah, so if we could look at our 6p, our elements that have 6p electrons, 6. These are our p, thallium to radon, right? Which one has a half-filled 6p subshell? What does that 6p subshell look like, do you know?
Has 3 orbitals, right?
That's right, 3 orbitals. So if I have half filled, there's only going to be 3 orbitals, 3 electrons in those 3 different orbitals.
Okay, so what does that mean?
It means that we end in 6p3, right? So that would be bismuth here, 6p3.
Oh, okay, I got it.
All right, 61. Which atom would be expected to have a half-filled 4s subshell?
That'd be potassium.
Okay, good, you got it. This is my 4s, 2 electrons to fill that subshell, and potassium just has 1 electron. Okay, write the electron configuration for the following atoms or ions. All right, so we start off with boron with a plus 3 charge. Boron by itself would be 1s2, 2s2, 2p1, right? If it has a plus 3 charge, it's lost 3 electrons. So now it's just, if I'm going to make this a plus 3, I need to get rid of 3 electrons. It's going to be just 1s2. You got that?
Yeah, I got it. Oxygen with a minus charge is going to have 1s2, 2s2, 2p, instead of 4, 5.
That's right, 2p5. Very good. Oxygen with a minus charge. Excellent.
Chlorine with a plus 3 charge. Can I do the noble gas?
Yeah, do the noble gas because there's lots of electrons in the core that aren't going to be impacted by this.
So neon,
Neon,
3s2,
good. 3s2.
3p. Wait, we lost 3 electrons?
Yeah, chlorine by itself would be 3p5, right?
Yeah, so 3p2?
That's right, 3s2, 3p2 is chlorine with a plus 3 charge. Okay, very good. Calcium with a plus 2 charge.
That would just be the noble gas electron configuration for argon.
Very good. So hopefully as everybody's comfortable, just that. I mean, that is going to be 1s2, 2s2, 2p6, 3s2, 3p6. That's what argon's electron configuration is. Okay, good. And then titanium.
Argon,
That's right, argon core,
4s2,
4s2.
and then 3d2?
That's right, 3d2. Good. Remember that first D level is in the 4th row, but its n values are suppressed 1. Okay, very good. Based on their position in the periodic table, predict which is the smallest ionic radius. Magnesium, strontium, silicon, chlorine, or iodide. All right, so how do we look at size when we're thinking about atoms? These are all atoms.
Higher up is bigger, right?
You mean lower down?
Oh yeah, lower down is bigger.
That's right. Lower down is bigger. So helium is smaller than radon. And that's rough. That's easy to see because helium only has 2 electrons. Radon has 86. So there's going to be more electrons the larger you get. But remember that as we go from boron to neon, for example, we go across that row, our size doesn't increase. Why does our size not increase?
Because we're adding electrons, but they're all going in the same subshell, right?
That's right. They're all going in the same subshell. And so the addition of protons as we move to the right is more influential. That electron in the new orbital within the same subshell doesn't increase in size. So the protons begin to draw those electrons closer to the center and it decreases in size. So let's look at magnesium and strontium. What's bigger?
Oh, strontium's bigger.
All right. What about silica and strontium?
Yeah, strontium's bigger.
Good. Chlorine and strontium?
Strontium would have to be bigger, right?
Yeah, it's 2 full shells down below chlorine. And iodide. What would be bigger, strontium or iodide?
You said as you move to the right, you get smaller, right?
Yeah, so we'd still have to say that strontium was our biggest. Okay. Good.
But didn't it ask for the smallest?
Oh, the smallest radius. Predict which has the smallest radius. Okay, so strontium is the biggest. What one would be the smallest?
The highest up is silicon and chlorine,
Okay.
and chlorine's farther to the right, so chlorine.
Okay, very good. So silicon and chlorine or only have electrons in their third shell, or magnesium has it in the third shell too, doesn't it?
Yeah, it does, I guess. But you said as you move to the right, things get smaller, right?
Generally, things get smaller because, again, we're just filling up the same shell. We're not increasing. It's not getting larger and larger. Our model of a nucleus with electrons getting bigger and bigger like this isn't entirely consistent. I mean, there's actually nothing consistent about it. Sometimes you see online people drawing models like still orbital models like this, where they say this is the 1s and there's 2 electrons in it, and this is the 2. Well, they don't even say 1s; they just say 1. This is the 2, and the 2 has, well, this is the 2s with 2 electrons in it, and then this would represent the 2p, and it could hold 6 electrons in it. 1, 2, 3, 4, 5, 6. Too many electrons. So the 2p's are larger than the 2s, but it's not a good model. It's not a good model. It does other things for us, but in terms of predicting size, it's going to not going to help us, right? When we look at our atoms, like magnesium, for example, I have to think about that 3s. And then as I go from sodium to magnesium to aluminum, the 3p electrons here. All right. So if we look at this slide that I have here, right? So as you go from beryllium to boron, you see the electrons, the sizes actually decrease from magnesium to aluminum, slightly smaller, 160 to 143, right? Okay. If you go from, for example, cadmium to indium, your size increases, right? Mercury to thallium, your size increases along that subshell border. If I go from lanthanum to thallium, right, our size also increases slightly. Okay, so there's a couple of exceptions there, but generally across any of these rows, we get a decrease in size as we go to the right. All right, so okay, whoops. So 68. Based on their position in the periodic table, which has the largest? Lithium, rubidium,
Gotta be rubidium.
you think?
Yeah.
Yeah, NF and I. Oh, what's bigger, rubidium or iodine?
Rubidium.
Very good, rubidium. Based on their position in the periodic table, predict the smallest first ionization energy. First ionization energy is the energy required to remove an electron. All right. So let's think about this. Who do you think it would be harder to remove an electron from? Fluorine or iodine?
Well, you said something in class about parents and children.
Yeah, that's a good way to remember. And for that matter, we could do helium or radon, right? Helium is a family with how many children?
Two electrons, that's like two children.
That's right. And if I try to remove an electron from helium, it's going to be difficult, right? Because helium has only 2 electrons. It has 2 kids. It's keeping close watch on both of those kids. Radon has 86 kids, though. So if I removed one, it might be a little bit easier for me to take an electron away, right?
Yeah, okay.
And that's what the ionization energy is. It's an energy associated with taking an atom and creating a positive charge by removing an electron. They should have called it the cationization energy, right? Because I'm forming a cation, but they just called it the ionization energy. All right, so based on their positions, if I look at lithium and cesium, what do you think?
Cesium would be easier to remove.
That's right, cesium would be easier. So the smallest first one, ionization, is what we're looking for. Nitrogen, fluorine, and iodide?
Yeah, what is it going from left to right?
All right, that's a good question. If we look at our series going left to right, for example, boron going to neon, right? Which of these do you think is going to be harder to remove an electron from?
Oh, probably the noble gas.
Yeah, I think you're right. So neon has 10 electrons. It receives a significant amount of stability, right? It's the smallest. The electrons are closest to the nucleus, the parents. The children are closest to the parents. They're going to be watched carefully, all right? Boron has fewer kids, yes, but it's already a little bit disheveled, right? So ionization energies increase as we go up, requires more energy as we go up, and increases as we move to the right. Okay, ionization energy trends. You see, it's not completely straightforward. There are spots where things get a little dicey in terms of ionization trends. The larger atoms, where electrons are all relatively far away, follow smoother patterns in their p block here. The smaller ones, there's a little bit of up and down, right? Across the d block here, you see disturbing trends that are hard to kind of identify. With more electrons, it's a little more smooth, but still it's not completely straightforward. But in general, we still think of ionization energies increasing as you move to the right and going up. Now, this is an important difference here, nitrogen and oxygen, and we use that as an example. But yeah, so we're not expected to memorize any of this stuff in terms of the actual specifics, just to know that the general trend is to the right and up with lots of exceptions, okay? Okay, so periodic table and slides. Writing. All right, so if we look at nitrogen, fluorine, and iodide, those are all going to be, nitrogen and fluorine are going to be very difficult to remove electrons from. Comparing cesium to iodide, cesium is going to be easier still, especially because iodide wants to gain an electron and cesium wants to give up an electron, right?
Okay.
All right, so what is the smallest first ionization energy? Cesium. Atoms of which group in the periodic table have a valence shell electron configuration of Ns2 Np3? What is this talking about?
Well, 3 electrons in the p orbital. So that's like nitrogen, phosphorus, What is that?
Arsenic.
Arsenic, antimony. Is that right?
That's right. Good. So we have NS2, our S is full, and we have 3p electrons, right? So this is 2p3, 3p3, 4p3, 5p3, so forth. Based on their position in the periodic table, list the following atoms in order of increasing radius: magnesium, calcium, rubidium, and cesium. Okay. Which one is going to be just our atoms? So magnesium, calcium, rubidium, and cesium. Magnesium, calcium, rubidium, and cesium. What's going to be the largest?
I think it's got to be cesium and then rubidium.
Right. So largest to smallest. Oh, increasing order, they wanted smallest to largest. That's all right. Largest is easy to pick out. Cesium, and then rubidium, and then what?
Then isn't it just calcium and magnesium?
That's right. So magnesium is the smallest, calcium is next. All right. Size going up and down like that is really straightforward. All right. What atoms or ions are isoelectronic with these species? For which atom and or ion is our isoelectronic with Br+? Okay. So we want to know those species that have the same electron configuration as Br+. Should we write down the electron configuration for Br+?
Was that plus one electron?
No, it's actually the electron configuration for Br with losing an electron, right?
Oh, okay.
So it's argon. Then what?
4s2, 3d10, 3p7.
That's right. So 4s2, argon core, 4s2. We're looking for bromine, right?
Yeah.
4s2, 3d10, 4p, 1, 2, 3, 4, 5.
Did I say 5? I think I said 7.
Yeah, 4p5 here. Okay, and that's bromine. Now with the plus charge, it's going to be 4p4 here. 4p4. So what else has that electron configuration? 4s2, 3d10, 4p4. 1, 2, 3, 4. That's a selenium atom, right?
Oh, that's an answer, huh?
Yep, that's it. That's all. Okay, which atom or ion is, yeah, R. So R, so there's possibly more. So let's see. Oh, isoelectronic. Sorry, isoelectronic also means it has similar properties in terms of the number of valence electrons. So I'm looking for something that has any S2 and any NP4. Okay, so definitely selenium. And then also arsenic with an extra electron. That one is going to have that same isoelectronic. Gallium with, if it had 3 extra electrons, that would be right. But losing 3 electrons, that's not going to be right. That's just going to be, yeah, it's not going to be right. So chlorine with an extra electron, that's not going to be right either. But selenium and arsenic with an extra electron should be our answers there. 81, compare both the numbers of protons and elements or electrons present in each to rank the following ions in order of increasing radius. All right, so radius. Arsenic with 3 extra electrons, bromine with 1 extra, potassium that's lost an electron, and magnesium that's lost 2. All right. So we talked a little bit about parents and children and comparing protons to the parents and electrons to the children. Remember that?
Yeah.
So what did we say with arsenic minus 3? Arsenic had 33 kids, and now we've removed 3. What does that do to its size?
Removing children makes it smaller.
Yeah. So if I have my parents, right, here they are walking down, I don't know, some street or in the mall somewhere, a group of parents, and there's the electrons roaming all over the place, right? the more parents there are to tell the electrons, hey, come close, stay away from that, don't touch that, it draws them in closer, right? So no, which one? Arsenic. If arsenic has 30 parents and they're trying to gather 33 parents and is trying to gather 33 children, it'll take a certain radius. But when you remove 3 of those children, then it's easier for these 33 parents to draw them in, right? The nucleus can distribute its charge over fewer electrons, and so they all feel what we call a stronger effective nuclear charge. So it will shrink. Okay? So there we have 33 protons and only 30 electrons. Whereas with bromine, we have bromine minus, we have 35 protons. Oh, no, sorry. Minus 3, we gain 3 electrons. Sorry, so we don't have 30 electrons, we have 36 electrons.
Yeah, I was going to say, I don't understand what's going on there.
So 36 electrons. Here we have 35 protons, but bromine has a negative charge. It has 36 electrons. For potassium, we have potassium. Is that really what they wanted to say? I think they meant to say rubidium. But for potassium, we have 19 protons. That's not going to, well, let's see, 19 protons. Yeah, 19 protons and 18 electrons. Okay, and then magnesium, 12 protons, and plus 2 charge, we have 10 electrons. All right, well, I mean, this is obviously going to be the smallest. This is going to be the second smallest. These two here are the only ones that are kind of up for grabs. What do you think?
If you have...
Sorry, I didn't realize you couldn't see very well. So this is going to be the smallest. It has 12 protons and 10 electrons, so 10 is much smaller than 18 or 36. 18 is going to be much smaller than 36. But if I have 36 electrons in both of these, which one is going to be the smallest? It's going to depend on the what?
The protons. So the 35 protons, which is the bromide ion, has more electrons, or protons, so it's going to draw them in closer.
That's right. So this is going to be the smallest. This one here is going to be the largest because it has 36 electrons but only has 33 protons. This has 36 electrons and 35. So smallest, first smallest, second smallest, third smallest, and that's the largest. All right, good stuff.
Thank you.